Major Walter Tulloch pulls the B-52 into a shallow turn over North Carolina at 0012 hours, 17 hours into a Chrome Dome patrol, when his fuel gauges show the right wing losing 5,000 pounds per minute. Behind him in the bomb bay ride two Mk-39 hydrogen bombs, each 260 times more powerful than Hiroshima, live and fully assembled. The co-pilot's hand moves to the crossfeed valves, trying to balance fuel across the wings, but the leak is catastrophic. Tulloch feels the yoke fight him as the aircraft begins an uncontrollable roll to the left. At 10,000 feet over farmland, the airframe stress exceeds limits no checklist anticipated. Earlier that day, at 0700 hours on 24 January 1961, Tulloch's B-52G had lifted off from Seymour Johnson Air Force Base in eastern North Carolina. The mission was routine, a 24-hour airborne alert loop over the eastern seaboard, part of Operation Chrome Dome. Strategic Air Command kept bombers aloft around the clock so a Soviet first strike could not destroy America's nuclear deterrent on the ground. Each aircraft carried live weapons and refueled in midair. Tulloch's crew of 6 settled into the patrol rhythm, knowing they would not touch ground again until the next morning. In the forward bomb bay, 2 Mark 39 thermonuclear weapons hung from steel shackles, each weighing 7,600 pounds and stretching 12 feet nose to tail. The Mark 39 was a 2-stage hydrogen bomb. A plutonium fission primary triggered a lithium deuteride fusion secondary, yielding 3.8 megatons. That was 260 times the force that destroyed Hiroshima. The weapons were not inert training shapes. They were fully operational, ready to deliver strategic firepower on command. Between storage and detonation stood 4 independent mechanical safety interlocks, a design philosophy that assumed bombers would fail gracefully, not catastrophically. By midnight, the crew had completed mid-air refueling and crossed the northern edge of the patrol box. Tulloch began a shallow right turn to start the southbound leg home. The aircraft was heavy with fuel, stable, and on autopilot. The navigator marked the turn on his plotting board. In the rear compartment, the gunner monitored tail radar. Everything was nominal until the fuel quantity indicators on the engineer's panel spiked downward. The number 5 tank in the right wing was hemorrhaging fuel into the slipstream, and the rate was accelerating. The leak was not a slow seep, but a rupture. Likely a failed valve or cracked fuel line dumping JP4 jet fuel at 5,000 pounds per minute. The co-pilot opened crossfeed valves to transfer fuel from other tanks and balance the load, but the system could not keep pace. The right wing grew lighter, the left wing heavier, and the B-52 began to roll left despite full right aileron. Tulloch disengaged the autopilot and fought the controls manually. He radioed Seymour Johnson to declare an emergency, but the aircraft was already out of equilibrium. At 10,000 feet, the fuel imbalance became unrecoverable. The left roll steepened despite Tulloch applying full right aileron and right rudder. Aerodynamic loads on the wings exceeded the structural limits of a bomber designed for steady cruise, not violent maneuvering. The aircraft began to buffet, then shudder. Tulloch could feel the yoke going mushy in his hands, the hydraulics losing pressure as the airframe twisted. The B-52 was coming apart in the air, and the crew had no procedure for what came next. The left wing separated first, tearing away at the root in a shower of sparks and fuel mist. The fuselage pitched nose down and began to tumble, pulling 3 to 4 G loads in multiple axes. Metal screamed as the bomb bay doors ripped open under aerodynamic pressure. Tulloch had seconds to make the call. He keyed the intercom and gave the order. Bail out. 3 crew members pulled ejection handles, 2 others unstrapped and moved toward manual bailout hatches. The B-52 broke into pieces over the dark Carolina farmland, scattering wreckage across 5 miles. 3 ejection seats fired successfully, blasting crew members clear of the spinning wreckage. 2 more bailed out manually through the lower hatch, tumbling into the freezing January air before pulling their ripcords. 5 men descended under parachute canopies, watching the burning pieces of their bomber spiral toward the ground below. 1 crew member's ejection seat malfunctioned, he did not survive. By the time the survivors touched down in tobacco fields and pine woods, the two Mk-39 weapons had already fallen free, tumbling through the darkness toward impact. Strategic Air Command emergency procedures covered controlled weapon jettison over open ocean or unpopulated desert, scenarios where the aircraft remained flyable and the crew could input commands through the bombardier's arming panel. No checklist existed for ejecting live thermonuclear weapons during uncontrolled flight over American farmland. The Mk-39 was designed to be jettisoned in stable flight, not released from a tumbling fuselage breaking apart at 10,000 feet. Tulloch and his crew had no way to disable the weapons remotely once aircraft systems failed, and no time to attempt manual safing before bailout. Each Mk-39 weapon carried 4 independent mechanical interlocks between safe storage and nuclear detonation. First, a ready safe switch that physically blocked the arming circuit. Second, the cockpit arming panel, requiring deliberate input from the bombardier. Third, a high-voltage thermal battery, a pyrotechnic device that generated 400 volts to fire the warhead, activated only on command. Fourth, a low-voltage arm safe switch that closed the final connection to the detonator bridge wire. All 4 had to fail or close in sequence for the weapon to detonate. The design assumed that multiple independent failures were vanishingly unlikely. Once the bomb bay doors tore open and the weapons fell free, the crew had no way to verify their status or command them to remain safe. The safety interlocks were purely mechanical, with no electrical monitoring or remote override. In a controlled jettison, the bombardier would confirm that the arming panel remained in safe mode and that the ready safe switch stayed locked. But in an uncontrolled breakup, with hydraulics lost and electrical systems severed, the weapons became autonomous. Their behavior depended entirely on the mechanical integrity of switches, springs, and relays subjected to forces the designers never anticipated. At 5,000 feet, the left wing separated completely, cartwheeling away from the fuselage. The remaining structure pitched nose down and accelerated, pulling 3 to 4 G-loads in a violent spin. Rivets popped, fuel tanks ruptured, and the bomb bay doors, already damaged, were ripped entirely off their hinges by the slipstream. The 2 Mark 39 weapons, each secured only by mechanical shackles designed for stable flight, broke free. Weapon 1 fell nose first. Weapon 2 tumbled sideways, spinning on multiple axes as it dropped toward the winter farmland below. Tulloch keyed the intercom one last time and gave the order to abandon the aircraft. The navigator, bombardier, and tail gunner pulled their ejection seat handles. Explosive charges fired the seats up and clear of the tumbling wreckage. The co-pilot and another crew member scrambled to the lower hatch, released it, and jumped into the black void, free-falling before deploying their parachutes. Tulloch stayed at the controls until the last possible moment, then ejected himself. His seat malfunctioned, but he survived. One crew member did not. By the time the survivors landed, the weapons had been falling for nearly 30 seconds. Weapon 1 stabilized nose down as it fell through 15,000 feet. A barometric sensor inside the weapon, calibrated to deploy the recovery parachute at that altitude, triggered a lanyard release mechanism. A 28-foot diameter parachute blossomed above the weapon, arresting its descent to roughly 20 feet per second. The system was working exactly as designed. The parachute would allow safe recovery of an intact weapon after deliberate jettison. But this was not a controlled release. The descent forces and parachute suspension loads were about to trigger a cascade the designers never anticipated. Weapon 2 had no such stable descent. It tumbled end over end, spinning on multiple axes, its parachute failing to deploy or tangling immediately. The weapon plummeted toward the waterlogged soil of a tobacco field near the town of Faro, North Carolina. It would later be found partially buried, its secondary safety mechanisms still engaged. Weapon 2 would not come close to detonation, but Weapon 1, descending slowly and smoothly under a fully deployed parachute, was about to cross the first safety threshold, then the second, then the third. The parachute suspension lines applied steady tension to the weapon's nose assembly. That tension actuated a mechanical lever inside the casing, the ready safe switch. In normal operation, the switch remained physically locked in the safe position, blocking any electrical path to the arming circuit. But the parachute deployment forces rotated the lever from safe to ready, closing the first relay in the firing sequence. The system behaved exactly as intended for a deliberate weapon drop. It had no way to distinguish a controlled jettison from a catastrophic accident. First safety bypassed. The cockpit arming panel circuit, normally requiring the bombardier to close a switch under controlled conditions, was designed to tolerate minor electrical transients. But during the breakup, structural shock or stray voltage from severed wiring harnesses closed the relay. Investigators would later find the panel circuit in the closed position, though the exact cause remained unclear from the wreckage. Whether it was mechanical shock, a short circuit, or voltage surge, the result was the same. The second interlock had failed. The firing circuit was now 2 steps closer to completion. The high-voltage thermal battery was a pyrotechnic device, a squib that generated 400 volts of firing current when initiated. It was supposed to activate only on receipt of a valid arming signal, a deliberate command from the bombardier. But post-recovery examination showed the battery had fired during descent, most likely from mechanical shock transmitted through the weapon's structure or from a short circuit in the damaged wiring harness. With the battery expended, 400 volts now sat ready across the X-unit capacitors, awaiting only the closure of the final switch to send current to the detonator bridge wire. 3 of 4 safeties had failed. With 3 interlocks bypassed, the firing circuit was complete except for the closure of a single low-voltage arm safe switch. This was a simple single-pole double-throw toggle spring-loaded to the safe position, controlling the final connection between the X-unit capacitors and the detonator bridge wire. It had no backup, no redundancy, and no electrical interlock. If impact forces jarred that toggle from safe to arm, closing the circuit, 400 volts would flow to the bridge wire, vaporizing it in microseconds and initiating the explosive lenses. The weapon was one mechanical movement away from full arming. The ready-safe switch was a mechanical lever physically linked to the parachute lanyard. In the safe position, the lever blocked the electrical path to the arming circuit, an open contact with no current flow. When the parachute deployed and the lanyard pulled taut, it rotated the lever to the ready position, closing the first relay. The mechanism assumed parachute deployment meant the weapon was being deliberately recovered after a controlled jettison. The lever had no sensor to detect crew intent, airframe integrity, or altitude. It responded only to tension. In Weapon 1's uncontrolled descent, the parachute worked perfectly, and the lever dutifully moved to ready. The cockpit arming panel was an electrical relay controlled by a switch on the bombardier's console. Normally, the bombardier would close the switch only during a deliberate weapon release, sending current to the second stage of the firing circuit. The panel was designed to tolerate minor voltage transients, brief spikes or drops, without closing unintentionally. But during the B-52's violent breakup, either mechanical shock jarred the relay into the closed position, or a short circuit in the damaged wiring harness created a false arming signal. Post-recovery examination of Weapon 1 found the arming panel circuit closed. The exact cause could not be determined from the wreckage, but the result was unambiguous. The second interlock had failed. The high-voltage thermal battery was a pyrotechnic generator, a sealed cylinder containing a chemical squib that, when ignited, produced a 400-volt pulse in less than a second. It was supposed to fire only on receipt of a valid arming command from the cockpit, but Weapon 1's battery fired during descent, likely from mechanical shock traveling through the weapon's aluminum casing or from a short circuit in the wiring. When investigators opened the weapon, they found the battery expended, its squib burned out, and the X-unit capacitors fully charged. That 400-volt pulse was now live, sitting across the firing circuit, held back only by the final arm safe switch. The low-voltage arm/safe switch was a simple stamped steel toggle, about the size of a thumbnail, controlling a single electrical contact. In the safe position, a spring with roughly 8 ounces of tension held the toggle open, physically preventing current from flowing to the detonator bridge wire. The toggle could move a quarter of an inch from safe to arm, closing the contact. It had no backup mechanism, no redundant path, and no electrical lockout. If impact shock jarred the toggle hard enough to overcome the spring tension and flip it to arm, the circuit would close, current would flow, and the bridge wire would vaporize, initiating the explosive lenses. With the ready safe switch closed, the arming panel circuit completed, and the thermal battery fired, the firing sequence was live. 400 volts sat across the X-unit capacitors, waiting for the final switch to close. The weapon's trajectory was stable under parachute, descending at 20 feet per second toward waterlogged farmland. Impact was seconds away. If that final toggle moved from safe to arm, whether from impact shock, ground collision, or structural deformation, the circuit would complete. Current would flow through the detonator bridge wire, vaporizing it in 600 nanoseconds and driving the explosive lenses inward to compress the plutonium primary core to supercriticality. 3 interlocks had failed. 1 remained. Weapon 1 struck waterlogged, tobacco-field soil at approximately 700 feet per second residual velocity, despite the parachute. The nose cone crushed on impact, compressing inward by several feet. The aluminum casing buckled. The secondary stage, filled with lithium deuteride fusion fuel, slammed forward against its internal supports. The plutonium primary core deformed under the deceleration load. Throughout the impact, the low-voltage toggle switch was subjected to shock forces in multiple axes. The spring tension held. The toggle remained in the safe position. The electrical contact stayed open. No current reached the bridge wire. The weapon did not detonate. If the toggle had closed, the firing sequence would have proceeded automatically. 400 volts would flow through the detonator bridge wire, a fine filament of platinum or tungsten. The wire would vaporize in 600 nanoseconds, creating a small explosion that drove the surrounding explosive lenses inward. 32 precisely shaped lenses would compress the plutonium primary core to supercritical density, initiating a fission chain reaction. The fission energy would ignite the lithium deuteride secondary, triggering thermonuclear fusion. The entire process, from bridge wire vaporization to megaton-scale detonation, would take less than a microsecond. But the toggle never closed. The sequence never began. Years later, Sandia engineer Parker F. Jones reviewed the weapon recovery data and wrote an internal memo that would remain classified until 2013. Jones concluded that the probability of the weapon remaining safe during the accident sequence could not be reliably determined. He noted that only one simple, low-voltage switch with a single spring had prevented detonation, and he described that outcome as fortuitous, not assured. The Mk-39 had been designed with 4 independent safeties, but the violent, uncontrolled nature of the B-52 breakup had defeated 3 of them in rapid succession. The final switch held, but it had no backup and no margin. The sun rose on 24 January 1961 over the tobacco fields and pine woods near Faro, North Carolina. Farmers driving to morning chores saw a parachute tangled in the tree line and a smoking crater in a field. One of them called the local sheriff, who radioed the Air Force. By 0900 hours, a recovery team from Seymour Johnson Air Force Base had cordoned off the site. They found Weapon 1 resting in a shallow impact crater, its nose crushed, its casing split along one seam, but largely intact. The parachute lay 200 yards upwind, snagged in oak branches. The recovery team approached Weapon 1 carefully, radiation detectors sweeping for contamination. The weapon showed no signs of radioactive release. The primary core and secondary stage were intact, their containment unbreached. Engineers disconnected the parachute harness, attached lifting straps, and used a crane to hoist the weapon onto a flatbed truck. They covered it with a tarp and transported it back to Seymour Johnson under armed escort. The weapon weighed 7,600 pounds, crushed and deformed, but still recognizable. Initial inspection revealed the arming panel circuit was closed and the thermal battery expended. Detailed diagnostics would follow. Weapon 2 had landed a mile away in a different field, and its impact signature was far more violent. It had tumbled without a stable parachute, striking the ground at full terminal velocity and burying itself deep in waterlogged soil. Recovery crews began digging, but at 50 feet the excavation flooded as groundwater poured in. Engineers attempted to pump the water out, but the soil collapsed inward, creating a muddy pit. After 8 weeks of effort, the Air Force halted the dig. The weapon's secondary stage and part of its plutonium primary core remained buried beneath the water table. Unable to recover Weapon 2, the Air Force negotiated a permanent easement with the landowner, purchasing the right to prohibit any deep excavation on the site in perpetuity. The plutonium core and thermonuclear secondary components remain buried there today, more than 60 years later, beneath a North Carolina tobacco field. A simple marker notes the easement. No public sign identifies what lies below. The groundwater has not been tested for contamination, and the Air Force has never disclosed the exact depth or condition of the buried weapon components. At Seymour Johnson, engineers opened Weapon 1's access panels and began a component-by-component inspection. They extracted the arming panel relay and confirmed it was in the closed position. They removed the thermal battery housing and found the pyrotechnic squib fully expended, the capacitors charged. They traced the wiring harness and documented damage consistent with structural breakup and electrical transient. Finally, they examined the low-voltage arm safe switch. It remained in the safe position, held by a spring with approximately 8 ounces of tension. The toggle had not moved. The firing circuit had never completed. The team lead compiled the findings and radioed Seymour Johnson Command. 3 of 4 safety interlocks had failed during the accident sequence. Only the final low-voltage toggle switch, with no backup mechanism, had prevented the weapon from arming fully. If impact forces had jarred that switch from safe to arm, the firing circuit would have completed. The message went up the chain to Strategic Air Command Headquarters. Within hours, SAC ordered an immediate review of all Chrome Dome weapon carriage procedures and safety protocols. No public statement was issued. The accident was classified. Investigators photographed the low-voltage arm safe switch in place before removing it for laboratory analysis. The images show a stamped steel toggle, roughly the size of a thumbnail, spring-loaded to the safe position, with a travel distance of 1/4 inch. The spring tension measured approximately 8 ounces. There was no redundant path, no backup switch, no secondary lockout. This single component, likely manufactured for a few cents in the late 1950s, had stood between routine Cold War deterrence patrol and a thermonuclear detonation over American soil. The photographs were classified and remained so for more than 50 years. Weapon 1 was transported to Pantex, the Department of Energy facility in Texas, where nuclear warheads are assembled and disassembled. Engineers dismantled the weapon, separating the plutonium primary, the lithium deuteride secondary, and the conventional explosive lenses. The fissile material was returned to the stockpile for reuse in other weapons. The Mk-39 casing and mechanical components were cataloged and stored. The specific weapon that came within one switch of detonating over North Carolina was retired from service. Its serial number struck from the active inventory. The Mk-39 design itself remained in the stockpile until 1966. Strategic Air Command moved quickly to reduce the risk of a repeat accident. Chrome Dome sortie durations were shortened, reducing crew fatigue and in-flight refueling requirements. SAC mandated additional mechanical interlock redundancy on all nuclear weapons carried during airborne alert missions. Engineers began designing fail-safe electrical arming systems with pilot-controlled lockout switches that could disable firing circuits even after structural failure. The doctrine of continuous airborne alert continued, but with tighter safety margins and more conservative weapon carriage protocols. The changes were implemented without public explanation. By 1966, the Mk-39 had been entirely phased out of the U.S. nuclear stockpile, replaced by newer designs with dual independent arming paths. Each new weapon required deliberate electronic input and mechanical confirmation from the crew before any firing circuit could be energized. Environmental sensing units were added to detect abnormal acceleration, freefall, or impact, physically disabling the firing circuits if the weapon left the aircraft under anything other than controlled jettison. The lessons of Goldsboro were embedded in hardware, not just procedures. The next generation of U.S. nuclear weapons incorporated permissive action links, or PAL systems, which required encrypted codes to arm the warhead. Without the correct code sequence, entered by the crew, the firing circuit remained physically disabled, regardless of the weapon's mechanical state. PAL systems added a layer of deliberate human control that could not be bypassed by structural failure, electrical transient, or mechanical shock. The technology was a direct response to accidents like Goldsboro, where passive mechanical safeties proved vulnerable to forces the designers never anticipated. Modern U.S. warheads are PAL-equipped as standard. The Goldsboro accident remained classified for more than 5 decades. No formal public acknowledgement of the 3 Interlock failure cascade was made until 2013, when documents were released under the Freedom of Information Act. Parker F. Jones's 1969 Sandia memo, which stated that only one simple low-voltage switch had prevented detonation and that the outcome was fortuitous, was among the released materials. The memo contradicted decades of official assurances that multiple independent safeties made accidental detonation impossible. The release prompted renewed scrutiny of Cold War weapons safety practices and the risks accepted in the name of deterrence. For decades, the public narrative held that multiple redundant safeties made accidental nuclear detonation vanishingly unlikely, a statistical impossibility. Goldsboro proved otherwise. 3 independent mechanical interlocks, designed by competent engineers and tested under controlled conditions, failed in rapid succession during a single uncontrolled crash. The 4th held, not because of superior design or deliberate redundancy, but because a spring-loaded toggle happened to remain in the safe position under impact shock. The accident revealed that the safety philosophy behind early Cold War weapons assumed failure modes far gentler than reality delivered. The low-voltage arm/safe switch that held in Weapon 1 was a simple stamped steel toggle, spring-loaded to safe, with no backup and no redundancy. It likely cost less than $1 to manufacture in 1950s dollars, perhaps as little as 50 cents. That toggle, with its 8 ounces of spring tension and 1/4 inch of travel, was the sole barrier between a routine chrome dome patrol and a 3.8 megaton ground burst. It held not because it was designed to withstand catastrophic breakup, but because impact forces happened not to jar it past its mechanical detent. Fortuitous, as Parker Jones wrote, not assured. A 3.8 megaton ground burst over North Carolina would have produced a fireball nearly 2 miles in diameter, with surface temperatures exceeding those of the sun's core. The initial thermal pulse would have ignited everything flammable within a 20-mile radius. The blast wave would have leveled structures for 10 miles in all directions. Radioactive fallout, driven by prevailing winds, would have contaminated more than 1,000 square miles, rendering the region uninhabitable for decades. Casualties would have numbered in the tens of thousands immediately, with long-term deaths from radiation exposure far higher. None of that happened because a spring-loaded toggle held in place. Operation Chrome Dome continued in modified form until 1968, when a B-52 carrying 4 hydrogen bombs crashed near Thule Air Base in Greenland, scattering radioactive debris across the ice. That accident, combined with the ongoing political and budgetary costs of continuous airborne alert, led the Department of Defense to suspend Chrome Dome entirely. The deterrent mission shifted to ground alert bombers and submarine-launched ballistic missiles, systems that did not require live weapons aloft 24 hours a day. Goldsboro had revealed the risks. Thule made them politically untenable. The era of continuous nuclear airborne patrol ended. Weapon 2 still lies beneath the North Carolina farmland, its plutonium core and thermonuclear secondary components never recovered. The Air Force has never publicly disclosed whether any fissile material has migrated into the groundwater, or whether long-term monitoring is in place. The easement remains in effect, prohibiting excavation. The land is farmed each season, tobacco and soybeans growing over a buried hydrogen bomb. It is a quiet monument to the risks of the Cold War deterrent posture, a risk accepted in secret and left unresolved beneath the soil. The accident happened more than 60 years ago, but its consequences are not entirely past tense. The Goldsboro accident forced a fundamental rethinking of nuclear weapon safety design. Modern U.S. warheads use permissive action links, environmental sensing units, and dual independent arming paths, all designed to prevent detonation under conditions far more severe than a single bomber crash. Those systems exist because a 50-cent toggle switch held in 1961, and because Parker Jones and his colleagues documented how close it came to failure. The accident was never publicly acknowledged as a near detonation until 2013, but its engineering lessons shaped every nuclear weapon designed since. The toggle is long gone, disassembled with Weapon 1 at Pantex. The doctrine it exposed remains embedded in U.S. nuclear policy to this day.